Good morning, everyone. It gives me immense pleasure to be here again for this lecture, which is Aircraft Stability and Control. I am Dr. Dwivedhi, Professor from Institute of Aeronautical Engineering, Hyderabad. As you know that from last few classes, I am discussing about aircraft stability and control. In the process of discussing aircraft stability and control, I have first gone with the history of aircraft, the manned power aircraft by the Wright brothers, the aircraft which has flown in 1903 December, Kitty Hawk, USA. In this aircraft, these two brothers, they are the first person who have flown the first controlled manned flight. Before that, no engines were used. Mostly people have used the glider, but these all things were uncontrolled. But the first flyers of Wright brother, this aircraft was really wonderful aircraft, and they have used the control of the aircraft. In previous class, I have discussed about the criteria for longitudinal static stability. So first we have to understand what is the stability. I am here talking about the aircraft static stability, not the other things. So I am taking this model here, and you can see that once aircraft is flying like this, wind is coming straight, no problem. As and when all of a sudden one gust came from any side, left, right, bottom, or in. I am assuming here the wind, all of a sudden some wind has come from the bottom, and it is come from here and hit like this, and it has gone up like this. So if the aircraft has gone up, whether the aircraft is coming to its original position or called equilibrium position, or it is going away from equilibrium position, or it is maintaining the disturbed position. So if this wind has gone, additional wind will be always there, but this gust wind, if it is removed, after removing the gust, whether this nose is coming, tending to come, it is not coming or not, it is not the question. When I talk about the static stability, it is not whether it is coming or not, we are not concerned. We are only concerned the tendency. Whether this aircraft, after disturbance, you remove the disturbing force, after removing of this force, if this aircraft nose is again tending to come towards its original position, then we can say that aircraft is statically stable. If the wind is hit from here and nose has gone up, but further nose is going, okay, so it is going like this, wind has come from this direction, nose has up, you remove this wind, but still it is going up, up, up. It is statically unstable. Means the tendency is to go away from its distant position also. Then we say it is a longitudinal unstable aircraft. The third case is once the aircraft is disturbed by the wind, whether this aircraft, it is flying like this, there is a disturbing force, it is like this, it is maintaining in the same type of motion, same angle, it is moving like this, same type of motion, then we can say that aircraft is neutrally stable. It is maintaining in the same condition which is obtained after disturbance. If it is like this, we can say that aircraft is neutrally stable. Okay, so these are the three conditions which we have to understand the today's topic. I have to discuss about the total aircraft lift. This we have to understand from the how much lift the aircraft is generating. In this aspect, I will try to discuss about something uh, about the lift. What is the lift? First, we have to understand what is the lift. Because if we talk about lift, we should know what is the lift. So assume this is the one airfoil. This is the your wind direction. This is from here to here. It is a chord line from which is touching from nose to. This is the chord line. So the angle between chord line is this, and this is called alpha, and this is called angle of attack. Angle of attack. Okay, so this is the velocity and this is the chord here. So the angle between the relative wind, direction of the relative wind, and the direction of the chord, the angle which is formed is called the angle of attack. So what is the lift? Because once we have to discuss the total aircraft lift, we should understand what is the lift first and how the lift is generated. If you see the aircraft, there are number of parts in aircraft and all are not taking part. Okay, just I will make here. This is the aircraft. These are the horizontal tail. These are the wings. I'm making one side only. And these are the here elevator. They are the ailerons. Okay, so here if you see, this is the fuselage. These are the wing. They are horizontal tail. Okay, and this is the vertical fin. This is the rudder. This is the elevator. These are the ailerons. Okay, so I have just shown something, but if you see here, the lift generating components are wings. The primary lift generating components are wings and then horizontal tail. These are the two components which are generating the lift, but this fuselage is a non-generating, it is not generating the lift. Okay, so these are the few components which used to generate the lift of the aircraft. So now I will say how the lift is generated. Okay, so if you see here, okay, just I will write here. This is the aerofoil and this is the chord line. So if you see here from here to here, these are the streamlines, and if you see that upper side, the area is reducing. So at the maximum thickness point, you have the highest acceleration or velocity. So assume this is your camber line. So this is your maximum T max. At this time max, you have the highest velocity, V max, in this point. So means what? From here to here, it is accelerating. Your flow is accelerating. You know, if the acceleration is there, force is equal to mass of air into acceleration. So this acceleration is there. It means there is a force, and this force is called the lift force. And after this, the Newton's third law also applied. It is a second law. So after this, what happened? This, it is going downwards. So a upward force is generated. If you use the Bernoulli's equation also, if the velocity is high, the pressure is P minus half rho V square is equal to constant. So if V is high, pressure will be low. So on upper side, velocity is more, pressure is less, but here pressure is P2 and here is a P1. So P2 minus P1 into area S is equal to lift force. So these are the three theories which I have explained you about how the lift is generated. So now I will talk about geometry for calculating the pitching moment derivative. So this is here diagram, and because you have to calculate the pitching moment, and this diagram is very, very important to understand how this aircraft parameters are set. Okay, so I will start from here at the nose. Just now I have discussed about alpha. Alpha is angle of attack. This angle of attack with respect to x. So this is the angle of attack, and here is the chord line. This one is the chord line. So this x into chord line is a IW. It is called the wing setting angle. Wing setting angle. This IW is a wing setting angle. Here, this is the wing, and here is the your center of gravity, and here is your aerodynamic center, and this is the center of gravity. All the measurements are taken from the leading edge. So AC, XAC, wing and fuselage, and from here XCG, the distance from here to here is XCG. And if you see here this horizontal tail, the aerodynamic center of the horizontal tail is from datum. Datum, we have taken the leading edge of the wing, and this is called XACH. The setting angle of your horizontal tail is plus IH, means nose is upward. If you see here a clear, this is the horizontal. So this thing is set like this. So this is called IH positive. And MAC, wing and fuselage, there is a moment of MAC, wing and fuselage. So here MAC wing is shown as a positive, but is usually negative. Here if you see, we have put this thing here. So it is showing here it is a positive. Here it is nose up is a positive and nose down is negative. So LH is the force or the lift force generated by the horizontal tail. Okay, so these are the things which we have to understand and we have to remember in the next classes. Here we have to see the calculation of angle of attack of the wing and the tail. So here if you see angle of attack experienced by the wing, alpha W is equal to alpha plus IW. Just you can see here. here in this diagram, if you see, this is the alpha from here and this is the IW. So total alpha W experienced by the wing, alpha plus IW. This is, so actually the wing will experience alpha W is equal to alpha angle of attack plus the wing setting angle IW. Okay. So it is shown here, and this angle of attack at the horizontal tail. What will happen at the horizontal tail? The horizontal tail will not feel the same angle of attack as it is experienced by the wing because of downwash. So if you see what is the downwash, just I am explaining here. This is the aircraft. Okay, so these are the wing here, and here is the tail. So here this wing is experiencing alpha W angle of attack, but you know what happened? This wing will go from here and it will downwash like this. So if you see here, this is the V infinity, which is going from here, it is a V infinity. So this V infinity is in this direction, but there is a downwash. This is the downwash. So actually your horizontal tail will experience VH velocity. So this VH, because here epsilon, this epsilon, how to calculate the epsilon? Epsilon is equal to epsilon naught plus d epsilon by d alpha into alpha. So this is the where alpha naught is a downwash angle at 0 aircraft angle of attack. So when alpha is equal to 0, so that time you will get epsilon naught. Angle of attack at horizontal tail, you will get, that is called alpha h. This alpha h is equal to alpha plus IH plus sigma E delta E minus epsilon. So what is this sigma E? It is called elevator effectiveness, and this is this tau E is equal to H divided by delta E. It means the angle of attack, the difference in angle of attack, it is a ratio of difference of angle of attack divided by deflection of elevator, change in elevator. So how much you are changing the elevator and how much your angle of attack is changed on the aircraft, that ratio is called tau E and it is called elevator effectiveness. So to calculate the angle of attack at horizontal tail, it is alpha. Alpha is the angle of attack which I have shown in the previous slide. IH is a horizontal tail setting plus tau E, delta E. Delta E is a deflection and tau E is delta H by delta E into epsilon, and this epsilon you can use this equation here, this one, to find this all things known, then you can get alpha H. So these are the very important parameters to understand that, to find this alpha H. Okay, so I think it is very much clear now. So how to find out epsilon? So this epsilon is equal to epsilon naught plus d epsilon by d alpha into alpha. So, and to find out angle of attack at horizontal tail, alpha H, here this epsilon is also required, tau E is required, IH, alpha, all this if you sum up, you will get the angle of attack for the tail. Now geometry description of elevator effectiveness. So if you see here this diagram shows how this thing is effective, and this effectiveness tau E, how to calculate the tau E. With the orientation of the relative wind and the front portion of the airfoil is staying fixed, and elevator deflection delta E produces change in the orientation of the chord line, which in turn changes the angle of attack of the airfoil. The larger the chord of the elevator is relative to the overall chord of the airfoil, the larger is tau E will be. So here I want to say that in this, the first diagram, if you see that this is the airfoil and there is no deflection of elevator, delta E is equal to 0, and here alpha 1 is equal to 5 degree. In this, tau E is equal to delta alpha H by delta E. So here it is a 5 degree. So here this and here if you see you have deflected this thing to 15 degree. Here it is a 0 degree, but here you have deflected to 15 degree only the elevator. Then the location of this thing is changed, and this you can see the angle of attack is now this much big. So it is now alpha 2 is equal to 10 degree. So 10 minus 5 is equal to 5, and 15 minus 0 is equal to 15. So tau E is equal to 1 by 3. So this, in this way we can calculate that as and when you increase the deflection, the effectiveness of this elevator tau E will be decreasing, larger. This will be much larger as you deflect the elevator. Okay, so elevator effectiveness, it is called the elevator effectiveness. If you increase the elevator, your angle of attack is automatically increased. Here you are increasing 15 degree, here alpha 2 is increased to 10 degree. Okay, so like this you have the effectiveness of the elevator can be calculated. So how to find out the y-axis? Y-axis is very important, and this you can see in this diagram. Just I want to see what is the y-axis, plus axis, and y-axis and the z-axis. So if you put your finger like this, that your thumb is towards the x, okay, thumb is towards the x, like x, right hand rule, thumbs towards the x, yeah, like this. Okay, so thumb is this, x, this is the x, this is the z, and this, and it is forefinger, it is called the plus y. So how the right wing, if you see, you are the pilot and x is towards the nose, that is called the x plus x. This is towards the earth, it is called the plus z. So your forefinger will be pointing towards the plus y. And another way we have to understand that aircraft, if you are the pilot and you are sitting on this aircraft center of gravity, towards your nose it is a plus x, towards your right hand it is a plus y, and towards the bottom is your plus z. So in this way we have to understand the direction of the. So how to now, this is the center of gravity here, this is the X, this is the Y, and here is the Z. Here this is the rotation, this is called the pitching, M is here pitching, and here Q is a pitch rate, and here is the V is the velocity, V is the velocity in Y direction. Here L is rolling moment, P is roll rate, U is the X velocity, X is in S direction, N is the yawing, R is yaw rate, Z is, and W is the velocity in Z direction. So these all parameters we have to understand that pitching will be with respect to Y axis, rolling will be with the X axis, and yawing will be with the Z axis. So I am again here, I will explain it. Aircraft is going like this. So if first I will discuss about the pitching. Pitching means this is the your Y axis. Y axis, with respect to Y axis, pitch will go, nose will go up or down. So this is called the pitching axis. This is the X axis. If it is rolling like this, roll will happen with respect to X axis. And this is the Z axis, nose will go left and right with respect to the Z axis. So like this we have to. So now if we want to calculate the total lift calculation, the total lift acting on the aircraft in terms of the two components. One is the fuselage, wing fuselage, and horizontal tail can be expressed as. So wing and fuselage we are writing as a WF, LWF plus LH cos epsilon. This epsilon is downwash angle, and we assume it is a very less. So what is the epsilon? I have just now explained. This is the velocity V infinity. Here is some downwash velocity V downwash I am writing. So the net you will get the velocity. This is called VH. This VH you will get, and here is the epsilon angle. So this angle, so total lift of the aircraft L will be the summation of the lift of wing and fuselage plus summation of the lift of horizontal tail cos epsilon. If epsilon is very small, okay, so we can say that cos 0 is equal to 1. So it is equivalent to LWF plus LH. This L we can write in coefficient form, because we have to write all the parameters in coefficient form or non-dimensionalized form. So here this L is equal to CL QS. Q is a dynamic pressure, half rho V square. So CL half rho V square S plus CLWF QS plus CLH QHSH. Okay, so here SH is a area of the tail and QSH is a your half rho V H square. Here we have to take this Q is equal to half rho V square H into SH. This we have to take in the care. We are not getting the same velocity as here. Here you will get half rho V square infinity S. But here you won't get that. Here you will get some other velocity, and this velocity will be lesser than the velocity which you are getting in the wing. Okay, so the dynamic pressure at the horizontal tail QH is equal to half rho V square H may be different than that acting on the wing fuselage because of the boundary layer and engine effect. So there is a boundary layer effect, engine effect. The dynamic pressure ratio, that is called NH, is used to describe the difference, that is NH is equal to QH by Q. So how much? Q is half rho V square HSH divided by half rho V square infinity into S. This can cut. So VH by V infinity square into SH by S. So this is called the dynamic pressure ratio. So here we can write in this way that CL is equal to CLWF plus CLH. If you divide by here by this, you will get what? NH into SH by S. Okay, so total coefficient of lift here, this you are going to get as sum of coefficient of lift of wing and fuselage plus CLH neta H SH by S. Okay, so these things we have to keep in our mind. And expanding CLWF and CLH using a familiar Taylor series and assuming IW is equal to 0. So here CLWF is equal to CL naught WF plus CL alpha WF into alpha. Okay, so it is CL naught. What is the CL naught? It is the coefficient of lift at 0 angle of attack and coefficient of lift of wing and fuselage at angle of attack. Same way, CLH is equal to CL naught H plus CL alpha H into alpha H. These equations 3 and 4, if we are putting in the equation number 2, which we have already seen that CL is equal to CL naught WF plus CL alpha WF. We are getting here CL naught WF plus CL alpha WF into alpha plus CL alpha H neta H SH by S, and this alpha H we have seen there that alpha minus epsilon plus IH plus delta E, tau E and delta E, and plus NH SH by S CL naught H. So this is the total coefficient of lift on the aircraft, total aircraft. You might have not seen in your previous courses, only you have seen about wing, you have seen about the this lift of the tail and all, but not as a total aircraft including your fuselage, your tail plane and all. So okay, so this is a detailed expression for the lift coefficient for the overall aircraft and is very useful because most of the parameters in it be calculated or estimated given the geometry of the aircraft. Okay, and this IB delta E, this all to be 0. So here this CL naught is equal to CL naught wing fuselage minus CL alpha H NH SH by S epsilon naught plus NH SH by S CL naught, and this we can say that this CL naught is equal to this, we can make it as a negligible, very small. So this CL naught is equal to CL naught of wing and fuselage. The approximation in equation 6 can be made if epsilon naught and CL naught H are very small. In the case of CL naught H, most aircraft use a symmetrical airfoil for the horizontal tail, and for this case CL naught H is equal to 0. So normally we are using the symmetrical aircraft so that this thing is 0. To obtain the CL alpha, the total aircraft lift curve slope, we simply take the partial derivative of equation 5 with respect to the alpha. So CL alpha is equal to CL alpha WF plus CL alpha H neta H SH by S 1 minus D epsilon by D alpha. CL IH and CL delta E are obtained through partial differential in a similar manner. So CL IH is equal to CL alpha H neta H SH by S. CL delta E is equal to CL alpha H NH SH by tau E. Okay. So, in summary, a detailed methods to approximate lift using a first order Taylor series expansion to obtain again put things in a respective, and remember that FAZ1S is equal to minus lift. So it is a minus CLQS. So minus CL naught plus CL alpha into alpha plus CLIH into IH plus CL delta E into delta T into QS. So in the next slide, figure presents wind tunnel data for the F-15B for the 4-tail configuration, and angle of attack range of 0 to 90 degree was evaluated. Notice that the maximum lift coefficient for each configuration occurs between 25 and 40 degree angle of attack. Also, the higher value of IH results in higher value of coefficient of lift. So this we can see here that the F-15B lift coefficient, the wind tunnel data are shown for IH at 0 degree. It is shown. It is a horizontal tail sitting angle at 0 degree. Then at a minus 15 degree. Then IH is equal to minus 30 degree. Then IH is equal to plus 15 degree. So you can see here that when IH is equal to 15 degree, this is the plot. This you can see. It means what? When the setting angle is positive, the coefficient of lift is highest at all angle of attack. When IH is equal to 0, this you can see here, the lift coefficient is very less. When IH is minus 30, you can see you are getting this. And when IH is equal to minus 15, you are getting this second one. So, if IH is positive, and what is the meaning of IH positive? Just I will explain. IH, incidence angle of, okay, just you can see here, this here, that incidence angle IH, this IH is positive, means this nose is upward like this. So 0, 5, 10. So if nose is upward, then it is a positive. So just I will show here also the so this is the IH0. Okay, and if you change it to like this, it is a this angle, it is a plus, whatever it may be, the 15 degree here. But if you make here, it is like this, nose down, it is a minus 15 degree. Okay, so like this, minus 15 means this nose is down. Nose is down, and here this nose is upward. So if the nose is upward, it is a plus, and if the nose is down, it is a minus. So if the nose is up, a huge amount of benefit you are going to get. This plot CL will be high. So if you want to make your better efficient your aircraft, you should place your tail in such a way that the angle of incidence it should be positive, so that it will create a positive lift and it will aid to the wing or total aircraft lift. Same way as the canards are there. In canards will always generate a positive lift, and this positive lift will be aided towards the total lift of the aircraft. So These are the references from Yachout I have taken, and this is the name of the book is Introduction to Aircraft Flight Mechanics, and it is AIAA Education series, and this is the thing. So hope you have understood in this the total lift, and this total lift is the contribution of the lift from the wing and fuselage plus the lift of the your horizontal tail. And this horizontal tail, the effect of horizontal tail, if it is set at a positive angle of attack, that IH is positive, then it will generate a positive lift and it will be added towards the total lift of the aircraft. So as a good designer, we have to see that the setting angle of the horizontal tail, it should be positive, and also the setting angle of the wing also it should be somewhat positive, so that we can get the positive angle of positive lift, and the total lift contribution will be increased. Okay, thank you very much for joining this.
Like, share and subscribe. Hit the bell icon for more updates.